So if any particle that experiences a force of gravitation in any field, we will call it as gravitational field. For example, if we throw anything up, what happens? It will come down because there is a gravitational force of attraction. We are bringing a particle from infinite position to this point. So that is why the limits are infinity and d. Hello everyone. Welcome to session 3 of chapter 8, Gravitation. This is Swati from Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. Dear children, in our last session, we had a discussion about the introduction part of the chapter Gravitation, where we have also studied what is law of gravitation. Newton proposed it and hence the name Newton's law of gravitation. Why it is called as universal law of gravitation. And also we have derived an expression which gives a relation between acceleration due to gravity as well as the gravitational constant. So in today's session, let us discuss more interesting concepts about gravitation. So in that, let us start with gravitational field. As I told in the last class itself, the gravity or gravitation, gravitational force, gravitational field, these are the words which are very much familiar to all of us. So in this chapter, we are going to know more about these terms. So what is the meaning of gravitational field? So what is the significance of gravitational field? So gravitational field is nothing but the region in which a particle experiences a gravitational force. So if any particle that experiences a force of gravitation in any field, we will call it as gravitational field. Or in simple words, we can say that the field where the gravitational force exists. So we will call it as gravitational field. So in the study of gravitational field, we have an important derivation for gravitational potential energy. So the expression for gravitational potential energy helps us in understanding many more concepts which are related to gravitation. So what is gravitational potential energy then? So we must know about the importance of this gravitational potential energy, and we will come to know by deriving its expression. Gravitational potential energy at any point in the gravitational field is nothing but the work done in displacing a particle from infinity to a given point. So let us derive an expression for gravitational potential energy. So you have to consider this diagram in understanding the concept that what is the work done in bringing a particle from one point to another point or from infinity to a particular point. So for that, let us consider this as Earth with mass m1. So O is nothing but the center and R is the radius of the Earth. The radius is from center to the surface. So R is the radius of the Earth. So P is any point in the gravitational field, and the distance between the center and the point P is d. Now let us consider a particle of mass m which is placed at a point A. So this is another particle whose mass is m which is placed at a point A. B is also another point in the gravitational field. The distance between A and B is considered as dx, a small separation. So it is dx. And the distance between the center of the Earth to this point where the particle is placed is considered as x. I hope the diagram is clear to everybody. Now we are deriving an expression for gravitational potential energy. So what is gravitational potential energy? In a gravitational field, the gravitational potential energy is nothing but the work done in displacing particle. So we have to find the work done in displacing particle from infinity to this distance or to this distance. So that we have to calculate. So to calculate the total work done, let us calculate or let us now analyze the work done in displacing a particle from small distance. Later, let us apply the same to bring the particle from a larger distance to one point. So before that, we have considered Earth as one mass and a particle as another mass. So there exists a force of attraction between these two masses, and from Newton's law of gravitation, we can write the expression for these two masses as F is proportional to the product of their masses, that is m and m, where the small m is nothing but mass of the particle, capital M is nothing but mass of the earth, divided by the distance between these two is x. So the square of the distance between them, and this can be written as F equals g into m divided by x square. Why? Because the symbol of proportionality is replaced by a constant called g, and it is nothing but the universal gravitational constant. So I will take it as equation 1. So now we have applied our Newton's law of gravitation between these two masses. Now we have to calculate what? Work done. So the work done in displacing a particle of mass m from point A to point B can be calculated by the formula. What's the formula to find the work done? It is force into displacement, and the displacement from this point to this point is nothing but dx. So F into dx. So let me take it as equation 2. Now we have written equation 1, that is Newton's law of gravitation, that is applied between two masses, and next we have to calculate the work done. So work done in bringing a particle to a very small distance we are calculating, that is from A to B. So that can be calculated with the formula F into dx. But we know what is F. From equation 1 we can write W is equal to, in the place of F, I am substituting this value g m divided by x square into dx. So I will take it as equation 3. So this is nothing but the work done dw, because this is the small work done in bringing a particle from A to B. Not from infinity to one particular point. We have taken a small distance, and hence it is dw, that is dmm divided by x square into dx. That's my equation 3. Now let us apply the same phenomena in bringing a particle from infinite position, that is from larger distance, to one particular point. So let us apply that. So that can be calculated by taking the integral parts of dx from infinity to a point D, which is nothing but w is equal to integral of dw. What is dw? It is nothing but the small work done in bringing a particle from A to B, that is a small distance. Now our aim is to find from infinite distance to this point, that is point D. For that, what we have to do? We have to integrate all dw's. So what are the limits? It is infinity to point D. We are bringing a particle from infinite position to this point. So that is why the limits are infinity and D. So by integrating small work done, we will get total work done, and hence it is W. But what is dW? Check in the previous slide. dW is nothing but gmm by x square into dx. So let us substitute the same. W is equal to infinity to D gmm divided by x square into dx. Now the gravitational constant is a constant. Mass of earth is not changing, it is also constant. Mass of particle is also a constant. So let us take all the constants outside, and we will write gmm integral of infinity to D 1 divided by x square dx. So now this is nothing but gmm integral of infinity to D 1 by x square can be written as x power minus 2 dx. Now let us apply the formula of integration to this. X power minus 2, it is of the form x to the power n. So x to the power n dx, which is nothing but x to the power n plus 1 divided by n plus 1. It's the standard formula as we all know. So now in the place of n we have minus 2. So let us apply the same formula in solving this. We will get x to the power minus 2 plus 1 divided by minus 2 plus 1. So we will get x to the power minus 1 divided by minus 1, which is nothing but minus 1 by x. So, let us substitute the same here. We will get GMM minus 1 by x infinity to d after integration. So, now what we have to do? So, we have to substitute the limits to the variable. So, let us substitute the limits to the variable. We will get GMM. Here we have minus 1 by x infinity to d. We can write this as minus GMM 1 minus x infinity to d. Here I have minus 1 by x, so I can write it as minus GMM 1 by x infinity and d are the limits. Now to apply the limits, we all know the formula, the rule, that is substitution of limits, that is upper limit minus lower limit. So that can be written as minus GMM 1 divided by upper limit is d minus 1 divided by, in the place of x I am substituting infinity. So what is 1 by infinity? It is 0. So this entire term becomes 0 and we will get minus GMM into 1 by d after the substitution. So now we can write it as minus GMM divided by d. This is the expression for total work done in bringing a particle from infinite distance to this point. Now, what will be the total work done in bringing a particle from infinity to center, which means the radius. So, this is r. So, what is the work done to bring to this point? So, now the expression can be modified in that case as W is equal to minus GMM divided by r. So, this work done is equal to gravitational potential energy. So, the gravitational potential energy is denoted by U, which is equal to minus GMM divided by R, where negative sign indicates that the work is done by a gravitational force. So, this is the expression for gravitational potential energy. So, our next concept is escape speed. What is escape speed? The name itself defines what is escape speed. It is nothing but the minimum speed with which a body is projected in order to escape from the gravitational force of the earth. For example, if we throw anything up, what happens? It will come down because there is a gravitational force of attraction. So, to escape this force of gravity of earth, what is the minimum speed required for a body? So, if the body want to escape from Earth's gravitational field, particular minimum speed is required for a body. So, that minimum speed with which the body is projected to escape from Earth's gravitational field. If it will not escape from Earth's gravitational force of attraction, it will come back again. In order to escape from the gravitational force, the body must be projected with certain minimum speed and we will call it as escape speed. For Earth, the escape speed is 11.2 km per second, the value of escape speed of Earth. So, what is escape energy then? What is the difference between escape speed and energy? So, escape energy is the minimum kinetic energy with which the body is projected in order to escape from Earth's gravitational force of attraction. So, if the body is moving, then it possesses some kinetic energy. The minimum kinetic energy of a body with which it can be projected in order to escape from gravitational force of Earth, we'll call it as escape energy, and it can be calculated with the formula half mve square. In this case, ve is nothing but escape speed of the projected body and m is its mass, where ke is nothing but kinetic energy. So, let us now write the expression for escape speed. So, according to conservation of energy, a body will escape from gravitational pull of Earth if the escape speed of the body is equal to gravitational potential energy on the Earth. If this escape speed and the gravitational potential energy on the Earth are equal, then the body will be escape from the gravitational pull of Earth. So, here let us write the expression for escape energy of a body. As I told you in the previous slide, escape energy is half mve square. So here I am substituting the same, which is equal to, we have derived the expression for gravitational potential energy on the Earth's surface, that is gmm divided by r, where m is the mass of the Earth and the small m is nothing but mass of the particle on the Earth. So here we need the expression for escape speed. So from this we can write, we need VE term, and I will retain the same to one side and I will bring all the other terms to the other side, which will be 2 will be multiplied to the numerator and we will get 2gm. Here m and m will get cancelled, divided by r. But we need a term which is for escape speed, that is VE. So here I have VE square. So if I want VE, I have to write it in square root. So VE is equal to square root of 2gm divided by r. But now we know the relation between acceleration due to gravity and gravitational constant, that is G equals gm divided by r square. Now we have gm divided by r here, and substituting g here, what we will get? By multiplying, dividing r on both numerator and denominator, we will get V is equal to root of 2gr. Because we have r square here, one r will get cancelled with the numerator and we will get root 2g into r, where g is nothing but acceleration due to gravity on the surface of Earth or any other planet. R is nothing but the radius of the planet which we consider. So this is the expression for escape speed, root of 2gr. By knowing the value of acceleration due to gravity and radius, we can find escape speed of the particle from that particular planet. So now let us derive an expression for energy of orbiting satellite. We all know that the satellites will revolve in its own orbit. So let us calculate the energy of the orbiting satellite. For this, let us consider one diagram that I will consider this as Earth with radius r. So it is having mass m. Let satellite is revolving around this Earth at certain height. So let us take, this is the point where the satellite is present. It is having mass m. So it is the orbit of the satellite. Let us consider it is there at a distance of h from the surface of the Earth. So I will consider the distance between the orbiting satellite and the center of Earth as d. So when the satellite is revolving around the Earth, it possesses both kinetic energy and potential energy. It possesses kinetic energy because of its motion and its potential energy due to its position. So the total energy of a satellite is nothing but the sum of kinetic energy plus potential energy. We have just derived an expression for gravitational potential energy. So I can even write it as gravitational potential energy. So what is the expression for kinetic energy? It is half mv square. So what is this v? That is nothing but the orbiting velocity, because the satellites will be in its own orbit, plus gravitational potential energy is given by minus g m divided by the distance between this point to this point, that is d. So I will call it as equation 1. So, but orbital velocity is v0 is equal to square root of gm divided by r plus h is what we have already derived. But in the above expression we need v0 square. So v0 square is nothing but squaring on both the sides of the above expression. We will get v0 square is equal to square and square root will get cancelled and we get gm divided by r plus h. Here in this expression, equation 1, d, I have d is nothing but r plus h. So I can write this equation 1 as, now equation 1 becomes, look at this equation, half m v0 square is nothing but gm divided by r plus h minus, I have gmm, here plus into minus will be minus. So gmm divided by, in the place of d I can replace r plus h. So now this expression can be written as half into m will get multiplied to the term inside the bracket. So gmm divided by r plus h minus GMM divided by R plus H. Now, what can we take outside, or what can we take the terms common? So, here you cannot cancel these two, it is multiplied with half. So, I can take GMM divided by R plus H common from these two terms, and I remain with 1 by 2 minus 1. So, it is 1 by 2 minus 1. So, this can be written as GMM divided by R plus H. Here in the denominator I will get 2. So, 1 minus 2, and we get the answer GMM divided by R plus H. Here 1 minus 2 is minus 1 divided by 2, or we can write it as minus GMM divided by 2 into R plus H. This is an expression for energy of orbiting satellite. Here negative sign indicates that the satellite is bounded to Earth's surface. It will not go out of the orbit. It says that it is bound to the Earth's surface. So, the expression for energy of an orbiting satellite is minus GMM divided by 2 into R plus H. So, in today's session, we have learnt a gravitational field, gravitational potential energy, expression for gravitational potential energy, and we have even derived an expression for energy of an orbiting satellite. Dear children, in the upcoming session, we will learn many more interesting concepts. Until then, keep learning all of you. Thank you.